Welcome to Sleepless History, where we explore the past in soothing detail to help you drift into peaceful sleep. I'm your host, and tonight we're embarking on a journey through the night skies of ancient civilizations. In this episode, we'll explore how our ancestors looked up at the stars, tracked the movements of celestial bodies, and built entire systems of understanding around the cosmos above them. This episode focuses on the history of astronomy in ancient civilizations. We'll travel from Mesopotamia to Mesoamerica, from the Nile Valley to the Indus River, discovering how different cultures observed, recorded, and interpreted the heavens. This is a story spanning thousands of years, filled with patient observation, mathematical brilliance, and the deep human need to understand our place in the universe. If you enjoy tonight's story, please don't forget to like the video and subscribe. It helps the channel more than you may think. Chapter 1: Mesopotamia, the cradle of astronomical observation. Our story begins in ancient Mesopotamia, the land between the Tigris and Euphrates rivers, in what is now modern-day Iraq. This region, often called the cradle of civilization, was also the birthplace of systematic astronomical observation. The clear night skies of Mesopotamia provided ideal conditions for watching the heavens, and the people who lived there took full advantage of this natural observatory. The Sumerians were among the earliest astronomers we know of, observing the skies as early as the 4th millennium before the Common Era. They developed a sophisticated understanding of celestial patterns, though much of their early work has been lost to time. What we do know comes from clay tablets that survived in the dry climate of the region, preserved for thousands of years beneath the sand. By around 3000 before the Common Era, the Sumerians had identified the 5 visible planets that could be seen with the naked eye. They called these wandering stars, distinguishing them from the fixed stars that maintained their positions relative to one another. These 5 planets were Mercury, Venus, Mars, Jupiter, and Saturn, though the Sumerians knew them by different names, associating each with various deities in their complex pantheon. The Babylonians, who rose to prominence around 2000 before the Common Era, inherited and expanded upon Sumerian astronomical knowledge. They were meticulous record keepers, and their astronomical diaries represent some of the most detailed observational records from the ancient world. These diaries, written on clay tablets in cuneiform script, tracked the positions of celestial bodies night after night, year after year, creating an invaluable dataset that would influence astronomy for centuries to come. One of the most significant Babylonian contributions to astronomy was their mathematical approach to predicting celestial events. By the 7th century before the Common Era, Babylonian astronomers had developed sophisticated mathematical models to predict the positions of planets and the timing of eclipses. These predictions were remarkably accurate, achieved through careful observation and mathematical analysis, rather than physical understanding of why celestial bodies moved as they did. The Babylonians divided the sky into constellations, many of which would later influence Greek astronomy and, through the Greeks, our modern system of constellations. They identified the zodiac, a band of constellations through which the sun, moon, and planets appeared to move. This zodiac was divided into 12 equal sections, each approximately 30 degrees wide corresponding to the 12 months of their calendar. The concept of the zodiac was intimately connected to the Babylonian calendar system. They used a lunisolar calendar, meaning it was based on both the cycles of the moon and the sun. Each month began with the new moon, and adjustments were made periodically to keep the calendar aligned with the solar year. This required careful astronomical observation and mathematical calculation, as the lunar and solar cycles don't align perfectly. Babylonian astronomy was not purely scientific in the modern sense. It was deeply intertwined with astrology and divination. The movements of celestial bodies were believed to reflect the will of the gods and to foretell events on earth. Kings employed court astronomers to watch the skies and interpret celestial omens. These omens might predict anything from the success of military campaigns to the flooding of the rivers to the health of the king himself. The astronomical compendium, known as the Enuma Anu Enlil, contained thousands of omens based on celestial phenomena. This massive work, compiled over centuries, represented the accumulated wisdom of Babylonian astronomical observation and astrological interpretation. It included predictions based on the appearance of the moon, the positions of planets, eclipses, and unusual atmospheric phenomena like halos around celestial bodies. One particularly important set of tablets is known as the Mul Appin, created around 1000 before the Common Era. These tablets contain a comprehensive catalogue of stars and constellations, organized by their rising and setting times throughout the year. The Mul Appin also includes information about the planets, mathematical schemes for tracking time, and rules for predicting weather based on stellar observations. The Babylonians were the first to recognize the Saros cycle, a period of approximately 18 years, 11 days, and 8 hours after which eclipses repeat in a similar pattern. This discovery allowed them to predict eclipses with remarkable accuracy. The cycle contains 223 lunar months, and after this period, the Sun, Earth, and Moon return to approximately the same relative positions, causing eclipses to recur in a predictable sequence. Babylonian mathematicians used a sophisticated number system based on 60, which we still use today when we divide hours into 60 minutes and minutes into 60 seconds. This sexagesimal system was well suited to astronomical calculations, as 60 is divisible by many numbers, making fractions easier to work with. The division of the circle into 360 degrees also derives from this Babylonian mathematical tradition. The Babylonian approach to astronomy was fundamentally arithmetical. They developed mathematical sequences and functions to predict planetary positions without necessarily understanding the physical mechanisms behind planetary motion. Their goal was prediction, not explanation, and in this they were remarkably successful. Their mathematical astronomy would later influence Greek astronomers who sought to add geometric and physical models to the Babylonian predictive schemes. By the 5th century before the Common Era, Babylonian astronomers had compiled extensive tables tracking planetary positions. These ephemerides, as they're called, allowed for the prediction of planetary locations years in advance. The accuracy of these predictions was sufficient for both practical calendar keeping and astrological purposes, demonstrating the sophistication of Babylonian mathematical astronomy. The Babylonians also paid careful attention to Venus, the brightest planet in the sky. The Venus tablets of Amisaduqa dating to around the 17th century before the Common Era, contain 21 years of observations of Venus's appearances and disappearances as it moved in relation to the Sun. These tablets represent some of the oldest astronomical records in existence, showing that systematic astronomical observation in Mesopotamia extends back nearly 4,000 years. Chapter 2: Ancient Egypt. Astronomy along the Nile. Let us now travel to ancient Egypt, where the regular flooding of the Nile River created one of the world's first great civilizations. Egyptian astronomy developed somewhat differently from Babylonian astronomy, shaped by the unique geographic and cultural context of the Nile Valley. The Egyptians were deeply concerned with timekeeping, particularly because the annual flooding of the Nile was so crucial to their agricultural cycle. They needed to predict when the floods would come, and astronomical observation provided the answer. The heliacal rising of Sirius, the brightest star in the night sky, coincided closely with the beginning of the Nile's flood season. This event occurred when Sirius first became visible on the eastern horizon just before sunrise, after a period of being hidden by the sun's glare. The Egyptians called Sirius Sopdet, and they associated this star with the goddess of the same name. The heliacal rising of Sopdet marked the beginning of the Egyptian year, typically occurring in mid-July by our modern calendar. This astronomical marker was so important that it formed the basis of the Egyptian civil calendar, which consisted of 365 days divided into 12 months of 30 days each, plus 5 additional days. The Egyptian calendar is one of the earliest solar calendars in human history. Unlike the Babylonian lunisolar calendar, the Egyptian civil calendar was based purely on the solar year, ignoring the phases of the moon. However, the Egyptians also maintained a separate lunar calendar for religious purposes, showing their recognition of both major celestial cycles. The discrepancy between the calendar year of 365 days and the actual solar year of approximately 365 and 1/4 days meant that the Egyptian calendar slowly drifted relative to the seasons. Over the course of 1460 years, called a Sothic cycle, the calendar would complete one full drift and return to alignment with the seasons. The Egyptians were aware of this drift, but they chose not to add leap days, possibly because the system's simplicity was valued over perfect accuracy. Egyptian astronomical knowledge is preserved in various forms, including temple inscriptions, tomb decorations, and documents written on papyrus. One of the most important sources is the astronomical ceiling of the tomb of Senenmut, dating to around 1500 before the Common Era. This ceiling depicts constellations, the northern circumpolar stars that never set below the horizon, and a lunar calendar showing the phases of the moon throughout the year. The Egyptians identified numerous constellations, though their system differed significantly from the Mesopotamian and later Greek traditions. Egyptian constellations included representations of animals, deities, and objects important to Egyptian culture. The hippopotamus, the crocodile, and various birds appear as constellations in Egyptian astronomical texts and tomb decorations. One distinctive feature of Egyptian astronomy was their use of decanal stars for timekeeping at night. The decans were 36 groups of stars, each of which rose above the eastern horizon at dawn for 10 days of the year, giving them their name. By observing which decan was rising, Egyptian astronomers could determine the time of year. During the night, the sequential rising of different decans allowed for the division of darkness into hours, creating what we might call the first star clock. The concept of dividing the night into 12 hours came from this decanal system. Similarly, the daylight period was also divided into 12 hours. However, because the lengths of day and night change throughout the year, these hours were not of equal length except at the equinoxes. Summer daylight hours were longer than summer nighttime hours, and vice versa in winter. These are called seasonal or temporal hours, and they were standard throughout the ancient world. Egyptian temples were often aligned with astronomical phenomena. The temple of Amun-Re at Karnak, one of the largest religious complexes in the ancient world, was oriented so that during the winter solstice, the setting sun would shine directly along the main axis of the temple, illuminating the inner sanctuary. This alignment connected the temple architecture with the cosmic order, emphasizing the pharaoh's role as an intermediary between the earthly and divine realms. The Egyptians also observed and recorded unusual celestial events. Papyri from the New Kingdom period mention comets, meteors, and eclipses, though these events were often interpreted as ominous signs rather than natural phenomena to be studied scientifically. The appearance of a comet might be seen as presaging disaster or significant change, reflecting the widespread ancient belief that celestial and terrestrial events were interconnected. Egyptian astronomy was closely tied to religion and mythology. The sky goddess Nut was often depicted as arching over the earth, her body spangled with stars. Each evening, Nut was said to swallow the sun, which would travel through her body during the night before being reborn at dawn. This mythological framework provided a narrative explanation for the daily cycle of the sun, integrating astronomical observation with religious belief. The northern circumpolar stars, which never set below the horizon in Egyptian latitudes, held special significance. These imperishable stars were associated with immortality and the afterlife. The pyramids and other royal tombs often had shafts or passages aligned with certain stars, particularly in the constellation we know as Orion, which the Egyptians associated with Osiris, the god of the afterlife. The southern shaft of the king's chamber in the Great Pyramid of Khufu, for example, pointed toward the belt of Orion when the pyramid was constructed around 2560 before the Common Era. Water clocks, or clepsydrae, were another Egyptian contribution to astronomical timekeeping. These devices measured time by the regulated flow of water from one container to another. The oldest known water clock dates to the reign of Amenhotep III in the 14th century before the Common Era. These clocks were marked with scales that accounted for the changing length of hours throughout the year, showing sophisticated understanding of seasonal variations in day length. The Egyptians also developed the merket, an instrument used to establish north-south lines and to observe the transit of stars across the meridian. The merket consisted of a wooden rod with a plumb line used in conjunction with a sighting tool to make precise astronomical observations. Teams of 2 priests would use merkets to track stellar positions and to align temple foundations with celestial directions. Egyptian astronomical knowledge influenced neighboring cultures and would eventually reach the Greeks during the Hellenistic period after Alexander the Great conquered Egypt in 332 before the Common Era. The city of Alexandria became a center of astronomical research, where Greek, Egyptian, and Babylonian astronomical traditions merged and evolved. Chapter 3: Ancient China, the Celestial Empire. Our journey now takes us eastward to ancient China, where a sophisticated and distinctive astronomical tradition developed largely independently of Western astronomy. Chinese astronomy has a documented history extending back more than 3,000 years, making it one of the longest continuous astronomical traditions in human history. The Chinese conceived of the heavens as intimately connected with earthly affairs, particularly with the legitimacy and effectiveness of imperial rule. The emperor was called the Son of Heaven, and his mandate to rule was believed to be reflected in celestial harmony. Unusual astronomical events like comets, eclipses, or planetary conjunctions could be interpreted as signs of heavenly displeasure, potentially threatening the emperor's legitimacy. This political dimension made astronomical observation a matter of state importance. From the Shang dynasty, beginning around 1600 before the Common Era, Chinese astronomers kept detailed records of celestial phenomena. Oracle bones from this period, used for divination, contain references to eclipses and other astronomical events. By the Zhou dynasty, beginning around 1046 before the Common Era, China had established an official bureau of astronomy responsible for maintaining the calendar, predicting eclipses, and interpreting celestial omens. The Chinese developed a sophisticated calendar system that was fundamentally lunisolar, similar to the Babylonian calendar, but developed independently. The Chinese calendar used lunar months, with each month beginning at the new moon. To keep the calendar aligned with the solar year and the seasons, intercalary months were added at regular intervals. The complex calculations required to maintain this system demonstrated advanced mathematical and astronomical capabilities. One of the most important roles of Chinese astronomers was to predict eclipses. The earliest recorded Chinese eclipse dates to around 1470 before the Common Era, mentioned in historical texts from the Shang dynasty. By the Han dynasty, beginning in 206 before the Common Era, Chinese astronomers could predict eclipses with reasonable accuracy, though the exact methods they used are not entirely clear from surviving records. Chinese astronomy was based on careful observation and meticulous record-keeping rather than mathematical modelling in the Babylonian style. Chinese astronomical records are among the most complete and continuous in the ancient world, providing modern astronomers with valuable historical data. Records of supernovae, novae, comets, meteor showers, and other transient phenomena have been particularly useful for contemporary astronomical research. The Chinese divided the sky into a system quite different from the Western constellation system. Rather than grouping stars into representations of mythological figures and animals, Chinese astronomers divided the sky into 4 quadrants, each associated with a mythological creature and a season. The azure dragon of the east represented spring, the vermilion bird of the south represented summer, the white tiger of the west represented autumn, and the black tortoise of the north represented winter. Within these quadrants, the Chinese identified 28 lunar mansions called Kao, which the moon passed through during its monthly cycle around the Earth. These mansions were unequal in size and served as a coordinate system for mapping the positions of celestial bodies. The system of lunar mansions may have originated as early as the Shang dynasty, making it one of the oldest astronomical coordinate systems still identifiable in historical records. Chinese astronomers also identified the circumpolar constellation we call the Big Dipper, which they knew as the Northern Dipper. Because the Earth's axis points roughly toward the North Celestial Pole, stars near this point appear to circle around it without setting below the horizon at Chinese latitudes. The Northern Dipper, being large and prominent, served as an important reference point for Chinese astronomical observation and for navigation. The pole star itself held special significance in Chinese astronomy and philosophy. Because it appears stationary while all other stars rotate around it, the pole star was seen as a symbol of the emperor, around whom the empire revolved. The emperor's throne room was often positioned so that he would face south, with the imaginary extension of his gaze reaching toward the celestial pole behind him, reinforcing the connection between earthly and celestial order. During the Han Dynasty, significant advances in astronomical instrumentation occurred. The astronomer Geng Shuchang, working around 50 before the Common Era, is credited with inventing the armillary sphere, an instrument consisting of metal rings representing the celestial equator, ecliptic, and meridian. This device allowed astronomers to measure the positions of celestial bodies with improved precision. Armillary spheres would become standard instruments in Chinese astronomy and would later be adopted by Islamic and European astronomers. Zhang Heng, one of the most accomplished astronomers of the Han Dynasty, lived from 78 to 139 in the Common Era. He created a rotating celestial globe that mechanically reproduced the apparent motion of the stars across the sky. This device was water-powered and represented a sophisticated integration of astronomical knowledge and mechanical engineering. Zhang Heng also attempted to estimate the number of stars visible to the naked eye, arriving at a figure of 11,520, a reasonable approximation given the limitations of naked eye observation. Chinese astronomers made detailed observations of comets, which were classified into various types based on their appearance. Comets with long tails, broom-like comets, and other varieties were distinguished and catalogued. The appearance of a comet was typically interpreted as an omen, with different types of comets predicting different earthly events. However, underneath this astrological interpretation was careful observational work that has proven valuable to modern comet researchers. One of the most famous historical astronomical observations from China is the recording of the supernova of 1054, which created the Crab Nebula. Chinese astronomers noted the appearance of a guest star that was bright enough to be visible during daylight for 23 days and remained visible at night for nearly 2 years. This detailed observation has helped modern astronomers understand the nature and history of supernovae. The Chinese also made systematic observations of sunspots, dark areas on the surface of the sun. Records of sunspot observations exist from as early as the 4th century before the Common Era. Chinese astronomers observed the sun through pieces of jade, or when its light was dimmed by mist, or through reflection in water, allowing them to see large sunspot groups without damaging their eyes. These observations represent the earliest systematic recording of solar phenomena. Chinese astronomy included sophisticated theories about the nature of the cosmos. The Huntian theory, developed during the Han Dynasty, proposed that the heavens were like an egg, with celestial bodies attached to an inner shell that rotated around the Earth. The Earth floated in the center of this sphere, like the yolk in an egg. This was one of several competing cosmological models in ancient China, showing that Chinese astronomers engaged in theoretical speculation about the structure of the universe, not merely observation and record keeping. The Chinese astronomical tradition was remarkably continuous, with knowledge passed down through generations of official astronomers. Imperial astronomical bureaus maintained extensive libraries of astronomical texts and observational records. When dynasties changed, the new dynasty would typically retain the astronomical bureau and its records, recognizing the value of this accumulated knowledge for maintaining the calendar and interpreting celestial phenomena. Chapter 4: Ancient India, Astronomy and Cosmic Cycles. Indian astronomy, known as Jyotisha, combined careful observation with elaborate mathematical models and deeply influenced astronomical development across Asia. The origins of Indian astronomy extend back to the Vedic period, beginning around 1500 before the Common Era. The Vedas, ancient sacred texts, contain references to celestial bodies and their movements. The Vedanga Jyotisha, a text on astronomy dating to around 1300 before the Common Era, discusses the movements of the sun and moon and provides rules for calculating the timing of religious ceremonies based on astronomical events. Indian astronomy was intimately connected with the need to establish proper times for religious rituals and festivals. The Hindu calendar is lunisolar, similar to the Babylonian and Chinese systems, with months based on the lunar cycle and periodic adjustments to maintain alignment with the solar year. The calculation of auspicious times for ceremonies, weddings, and other important events required detailed astronomical knowledge. The Indians conceived of time in vast cycles. The smallest unit of time in ancient Indian texts is the paramanu, defined as approximately 17 microseconds. At the other extreme, Indian cosmology describes kalpas, cosmic cycles lasting billions of years. This conception of immense timescales was unique in the ancient world and reflected sophisticated mathematical thinking about cycles and large numbers. One complete cycle of creation and destruction, called a kalpa, was said to last 4,320,000,000 years. This is remarkably close to the actual age of the Earth as determined by modern geology, though this similarity is coincidental rather than indicating ancient knowledge of Earth's true age. Nevertheless, the willingness to conceptualize such vast timescales shows the intellectual boldness of ancient Indian cosmological thought. Indian astronomers made careful observations of planetary motions and developed mathematical models to predict planetary positions. The Surya Siddhanta, an astronomical treatise whose current form dates to around 400 to 500 in the Common Era, but which contains earlier material, presents a detailed mathematical system for calculating planetary positions, eclipses, and other celestial phenomena. The Surya Siddhanta divides the zodiac into 12 signs and 27 or 28 lunar mansions called nakshatras. These nakshatras are similar in concept to the Chinese XEU, and there may have been cultural exchange between Indian and Chinese astronomical traditions, though each system was largely developed independently. The nakshatras were used to track the moon's position and were important for calendrical and astrological purposes. Indian astronomers calculated the length of the solar year with remarkable precision. The Surya Siddhanta gives a value of 365 days, 6 hours, 12 minutes, and 36.5 seconds for the length of the year. This is very close to the true value, differing by only a few minutes. Such accuracy required centuries of careful observation and mathematical analysis. Aryabhata, who lived from 476 to 550 in the Common Era, was one of the most influential astronomers in Indian history. His work, the Aryabhatiya, written when he was only 23 years old, contains sophisticated astronomical models and mathematical techniques. Aryabhata calculated the circumference of the Earth to be 24,835 miles, remarkably close to the modern value of approximately 24,900 miles. One of Aryabhata's most radical proposals was that the apparent motion of the stars across the sky was due to the rotation of the Earth on its axis, rather than the rotation of the celestial sphere around a stationary Earth. This heliocentric insight predated Copernicus by more than 1,000 years, though Aryabhata's view did not achieve widespread acceptance in India and was even more unknown in Europe. Aryabhata also provided a correct explanation for eclipses, understanding that lunar eclipses occur when the Earth passes between the Sun and Moon, casting its shadow on the Moon, and that solar eclipses occur when the Moon passes between the Earth and Sun, blocking the Sun's light. This physical understanding of eclipses was more advanced than the purely predictive models of many other ancient astronomical traditions. Indian mathematicians made fundamental contributions that supported astronomical calculations. The concept of zero as a number and the decimal place value number system were Indian innovations that revolutionized mathematics. The sine function, fundamental to modern trigonometry, was developed by Indian mathematicians for use in astronomical calculations. The Surya Siddhanta contains detailed sine tables used to calculate planetary positions. Brahmagupta, who lived from 598 to 668, was another major figure in Indian astronomy. His work, the Brahmasputa Siddhanta, contains corrections and improvements to earlier astronomical models. Brahmagupta also made important contributions to mathematics, including rules for arithmetic with zero and negative numbers, concepts that would not be accepted in European mathematics until much later. Indian astronomers built observational instruments called yantras to measure celestial positions and to verify their mathematical models. These instruments included gnomons for measuring the sun's shadow, water clocks for timekeeping, and various devices for measuring the positions of stars and planets. While earlier Indian astronomical instruments have not survived, later observatories from the medieval period show the continuation of this instrumental tradition. The concept of an astronomical observatory in India differed somewhat from observatories in other cultures. Observatories were often associated with temples and religious institutions, reflecting the close connection between astronomy and religious practice. Astronomical observations were used to maintain the calendar for religious festivals and to cast horoscopes, an important application of astronomy in Indian culture. Indian astronomy spread to neighbouring regions through trade and cultural exchange. Buddhist monks carried astronomical knowledge along with religious teachings into Central Asia, China, and Southeast Asia. Indian astronomical texts were translated into Arabic during the Islamic Golden Age, influencing the development of Islamic astronomy. Through this chain of transmission, Indian astronomical methods and mathematical techniques eventually reached medieval Europe. The nakshatra system was particularly influential across Asia. Similar systems of lunar mansions appear in Chinese, Arabic, and Southeast Asian astronomy, suggesting either a common origin or extensive cultural exchange. The word nakshatra itself appears in various forms in astronomical texts across Asia, showing the direct transmission of Indian astronomical terminology. Indian astronomers also observed and recorded unusual celestial phenomena. References to comets, meteors, and possible supernovae appear in ancient Indian texts, though these are generally less detailed than Chinese records of similar events. The interpretation of these phenomena was typically astrological, with such events seen as omens affecting human affairs, particularly the fates of kings and kingdoms. The astronomical tradition in India was not monolithic, but comprised various schools with different methods and theoretical frameworks. The Aryabhata school and the Brahma school represented two major approaches, with differences in their calculation methods and cosmological models. These schools engaged in scholarly debate and refinement of astronomical models, showing that Indian astronomy was a dynamic and evolving tradition rather than a static body of knowledge. Chapter 5: Ancient Greece: From Mythology to Mathematical Models. Greek astronomy built upon Babylonian and Egyptian foundations, but developed in distinctive directions, emphasizing geometric models and rational explanation of celestial phenomena. In early Greek thought, celestial bodies were associated with gods and heroes. The constellation patterns that we still use today largely derive from Greek mythology. The constellation Orion represented a great hunter, Ursa Major and Ursa Minor were bears, and the zodiacal constellations represented various mythological figures and creatures. These stories provided narrative frameworks for understanding the star patterns, even as Greek astronomy became increasingly mathematical. The pre-Socratic philosophers, beginning around 600 before the Common Era, began to seek natural explanations for celestial phenomena rather than purely mythological ones. Thales of Miletus, who lived from around 624 to approximately 546 before the Common Era, is said to have predicted a solar eclipse that occurred on May 28, 585 before the Common Era. Whether this prediction was based on Babylonian eclipse cycles that Thales learned during his travels, or was merely fortunate timing, is debated by historians, but the story illustrates the Greek interest in understanding and predicting celestial events. Anaximander, a student of Thales, proposed that the Earth floated freely in space, unsupported by any foundation. This was a remarkable conceptual leap, abandoning the common notion that the Earth must rest on something. Anaximander also suggested that the sun, moon, and stars were not divine beings, but natural objects, with the sun being a fire seen through an opening in a surrounding wheel of mist. While this model was incorrect in its details, it represented an attempt to provide naturalistic explanations for celestial phenomena. Pythagoras, who lived around 570 to approximately 495 before the Common Era, and his followers made important contributions to mathematical astronomy. The Pythagoreans believed that the cosmos was fundamentally mathematical and that celestial bodies moved according to mathematical principles. They recognized that the morning star and evening star were the same object, the planet Venus, which had been observed as two separate entities in earlier Greek thought. The Pythagorean school also proposed that the Earth was spherical rather than flat. Based on observations such as the curved shadow the Earth casts on the Moon during lunar eclipses and the changing appearance of stars at different latitudes. The spherical Earth would become standard in Greek astronomical thought, in contrast to the flat Earth models common in many other ancient cultures. Plato, who lived from approximately 428 to 348 before the Common Era, influenced astronomical thinking through his philosophical framework. Plato argued that the heavens were perfect and unchanging, with celestial motions being eternally uniform and circular. This philosophical commitment to perfection and mathematical order would shape Greek astronomy for centuries, leading astronomers to construct models using only uniform circular motions, even when observations suggested more complex movements. Eudoxus of Cnidus, a student of Plato who lived from approximately 408 to 355 before the Common Era, created the first mathematical model of planetary motion using a system of concentric spheres. In Eudoxus's model, each celestial body was carried on a sphere that rotated on an axis. Multiple spheres were nested together, with their combined rotations producing the observed motions of planets, including their apparent retrograde motion when they seemed to reverse direction in the sky. Eudoxus's model required 27 spheres in total to account for the motions of the Sun, Moon, and 5 known planets. While this model was geometrically elegant and satisfied the requirement for uniform circular motion, it did not perfectly match observations and could not account for the varying brightness of planets, which suggested that their distances from Earth changed over time. Aristotle, who lived from 384 to 322 before the Common Era, adopted and modified Eudoxus's concentric sphere model, increasing the number of spheres to 55 to better match observations. Aristotle's cosmological model placed Earth at the center of a spherical cosmos, with the Moon, Sun, planets, and stars arranged in concentric spheres around it. This geocentric model would dominate Western astronomical thought for nearly 2,000 years. Aristotle made a clear distinction between the terrestrial realm, where objects moved naturally in straight lines and were subject to change and decay, and the celestial realm, where objects moved in perfect circles and were eternal and unchanging. This philosophical framework influenced how astronomical observations were interpreted, with anomalies often attributed to observational error rather than to flaws in the theoretical model. Heraclides Ponticus, who lived from approximately 390 to 310 before the Common Era, proposed that Mercury and Venus orbit the Sun rather than the Earth, while the Sun orbits the Earth. This was a step toward a heliocentric model, though Heraclides maintained that the Earth was still the center of the cosmos. He also suggested that the Earth rotates on its axis once every 24 hours, explaining the apparent daily motion of the stars without requiring the entire celestial sphere to rotate. Aristarchus of Samos, who lived from approximately 310 to 230 before the Common Era, proposed the first fully heliocentric model, suggesting that the Earth and other planets orbit the Sun while the Earth rotates on its axis. This radical idea anticipated Copernicus by more than 1700 years, but it was not widely accepted in ancient Greece. The heliocentric model seemed to contradict everyday experience and lacked compelling observational evidence in the ancient context. Aristarchus also attempted to measure the sizes and distances of the Sun and Moon using geometric methods. By observing the angle between the Sun and Moon when the Moon is at half phase and using geometric reasoning, Aristarchus concluded that the Sun was about 19 times farther from Earth than the Moon and about 19 times larger in diameter. While his specific measurements were inaccurate due to observational limitations, his geometric method was sound and showed the application of mathematics to physical cosmology. Eratosthenes, who lived from approximately 276 to 194 before the Common Era, calculated the circumference of the Earth using an elegant geometric method. He observed that at noon on the summer solstice, the Sun was directly overhead in Syene in southern Egypt, casting no shadow from a vertical stick. At the same time in Alexandria, about 5,000 stadia to the north, a vertical stick cast a shadow indicating that the Sun was 7 degrees from vertical. Assuming the Earth was spherical and that the Sun was far enough away that its rays were essentially parallel when reaching Earth, Eratosthenes calculated that 7 degrees represented 1/50th of a complete circle. Therefore, the distance between Syene and Alexandria represented 1/50th of Earth's circumference. Multiplying 5,000 stadia by 50 gave him 250,000 stadia for Earth's circumference, equivalent to approximately 25,000 miles, remarkably close to the actual value. Hipparchus, who lived during the 2nd century before the Common Era, was one of the greatest observational astronomers of antiquity. He created a comprehensive star catalogue listing the positions of approximately 850 stars, classified by their brightness into 6 magnitudes. This magnitude system, with first magnitude being the brightest stars visible to the naked eye and 6th magnitude being the faintest, is still used in modified form in modern astronomy. Hipparchus discovered the precession of the equinoxes by comparing his own observations with earlier Greek observations and with Babylonian records. He found that the positions of stars relative to the equinoxes had shifted over time, with the equinoctial points moving slowly westward along the ecliptic. We now know this precession is caused by a wobble in Earth's axis, completing one cycle approximately every 26,000 years, though Hipparchus did not have access to this physical explanation. To explain the varying speeds of the Sun's apparent motion through the zodiac and the varying brightness of planets, Hipparchus developed mathematical models using eccentric circles and epicycles. An eccentric circle had Earth offset from the center of a planet's circular orbit, while an epicycle was a small circle whose center moved along a larger circle called the deferent. These geometric devices allowed models using circular motions to approximate the more complex actual paths of celestial bodies. Hipparchus also improved techniques for predicting eclipses, building on Babylonian methods, but adding Greek geometric understanding. He calculated the length of the lunar month to an accuracy of better than 1 second, and estimated the length of the solar year to within 6.5 minutes of the true value. His astronomical parameters would be used by later astronomers, including Ptolemy, whose work would synthesize Greek astronomy into a comprehensive system. Chapter 6: Ptolemaic Astronomy, the Classical Synthesis. Claudius Ptolemy, who worked in Alexandria during the 2nd century of the Common Era, created the most comprehensive astronomical system of antiquity. His great work, the Almagest, synthesized centuries of Greek and Babylonian astronomical knowledge into a unified mathematical framework that would dominate Western astronomy for nearly 1400 years. The Almagest, whose title comes from an Arabic translation meaning the greatest, contained a complete mathematical model for predicting the positions of the sun, moon, planets, and stars. Ptolemy built upon the work of Hipparchus and other earlier astronomers, but his comprehensive system went far beyond anything that had come before. The Almagest included star catalogues, mathematical tables, and detailed instructions for constructing astronomical instruments. Ptolemy's geocentric model placed the Earth at the center of the cosmos, surrounded by concentric spheres carrying the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and the fixed stars. This ordering was based on observed periods of revolution, with faster moving bodies assumed to be closer to Earth. However, the actual motions were more complex than simple circles could represent, requiring Ptolemy to employ sophisticated geometric constructions. To account for the varying speeds and apparent retrograde motions of planets, Ptolemy used a combination of deferents, epicycles, and equants. The deferent was the main circle on which a planet's epicycle moved. The epicycle was a smaller circle whose center travelled along the deferent, with the planet itself moving on the epicycle. This combination could produce paths that appeared to loop back on themselves, matching the observed retrograde motions of planets. The equant was Ptolemy's most controversial innovation. It was a point offset from the center of the deferent from which the epicycle appeared to move at uniform angular speed, even though it moved at variable speed relative to the Earth or the deferent center. The equant violated the Platonic principle that celestial motions should be truly uniform, not just apparently uniform from a particular point, leading to criticism from later astronomers who sought models using only truly uniform circular motions. Despite the theoretical objection to the equant, Ptolemy's models worked remarkably well for predicting planetary positions. The Almagest allowed astronomers to calculate where planets would appear in the sky months or years in advance, with unprecedented accuracy. This predictive success ensured the Almagest's influence, even as some philosophers objected to its theoretical foundations. Ptolemy also wrote on astrology in his Tetrabiblos, reflecting the close connection between astronomy and astrology throughout the ancient world. While modern science separates these disciplines, in Ptolemy's time they were intimately related. Astronomy provided the mathematical tools to calculate planetary positions, while astrology interpreted the meaning of those positions. Ptolemy saw both as legitimate applications of knowledge about the heavens. In addition to the Almagest, Ptolemy wrote works on geography, optics, and music theory, showing the breadth of ancient astronomical scholarship. His geography contained a catalogue of places with their latitudes and longitudes and instructions for map-making. While many of his geographic coordinates were inaccurate, the systematic approach to locating places on Earth's surface represented an important step in cartography. The astronomical instruments described in the Almagest included the armillary sphere, which could be used to measure the positions of celestial bodies in a coordinate system based on the celestial equator and ecliptic. Ptolemy also described the astrolabe, a sophisticated instrument that could be used to solve various astronomical problems, including determining the time at night from stellar observations and calculating the rising and setting times of celestial bodies. The preservation and transmission of Ptolemy's work occurred primarily through Islamic civilization. After the decline of classical learning in Western Europe, Islamic scholars translated the Almagest into Arabic during the 9th century. Islamic astronomers studied, critiqued, and attempted to improve upon Ptolemy's models, creating a sophisticated astronomical tradition that preserved and extended ancient knowledge. Chapter 7: Astronomy in the Americas. Independent Observations. Our journey now crosses the Atlantic Ocean to the Americas, where sophisticated astronomical traditions developed entirely independently of Old World astronomy. The civilizations of Mesoamerica and South America observed the same sky, but interpreted it through different cultural frameworks, creating unique astronomical systems. The Maya civilization of Central America developed one of the most sophisticated astronomical traditions in the ancient Americas. The Maya created accurate calendar systems, built observatories aligned with celestial events, and maintained detailed records of astronomical phenomena. Their astronomical knowledge served both practical purposes, such as agriculture and timekeeping, and religious functions. The Maya used multiple interlocking calendar systems. The Tzolk'in was a 260-day sacred calendar formed by the combination of 13 numbers and 20-day names. The Harb was a 365-day solar calendar divided into 18 months of 20 days each, plus 5 unlucky days at the year's end. These two calendars meshed together, creating a calendar round cycle of 52 years, after which the same combination of Tzolk'in and Harb dates would recur. The Maya also used the long count, a linear day count from a creation date corresponding to August 11th, 3114 before the Common Era in the proleptic Gregorian calendar. The long count used a modified base 20 number system with positions representing days, 20-day periods called uinals, 360-day periods called tons, 20-ton periods called katuns, and 400-ton periods called baktuns. This system allowed the Maya to record dates over thousands of years with precision. Maya astronomers made careful observations of Venus, tracking its appearances as morning star and evening star. The Dresden Codex, one of the few surviving Maya books, contains detailed tables tracking the 584-day Venus cycle. This cycle represents 5 Venus synodic periods, nearly equal to 8 Earth years, after which Venus returns to approximately the same position relative to the Sun and Earth. The precision of these Venus tables shows that Maya astronomers had observed and recorded Venus's motion for many cycles. The Maya built architectural alignments to mark astronomical events. At Chichen Itza, the pyramid known as El Castillo is aligned so that during the spring and autumn equinoxes, the setting sun creates a shadow pattern resembling a serpent descending the pyramid stairs. This alignment connected architecture, astronomy, and religious symbolism in a way characteristic of Maya civilization. The caracol at Chichen Itza is often identified as an observatory. This round building contains viewing windows aligned with various astronomical directions, including the northernmost and southernmost rising points of Venus. While the exact astronomical functions of the caracol are debated by scholars, the building clearly incorporated astronomical alignments into its design, suggesting its use for observing celestial phenomena. Maya astronomy was intimately connected with timekeeping and divination. The combination of different calendrical cycles created patterns that were believed to influence events and human affairs. The Maya consulted almanacs that correlated calendar dates with astronomical positions and with predictions about agriculture, weather, warfare, and other important matters. This integration of astronomy with divination was similar to approaches in Mesopotamia, China, and other ancient civilizations. The Maya were also aware of eclipses and could predict them to some extent. The Dresden Codex contains eclipse tables covering a period of more than 33 years, suggesting that Maya astronomers recognized the Saros-like cycles that govern eclipse occurrences. While their eclipse prediction methods may not have been as sophisticated as those of Babylonian or Greek astronomers, they show careful long-term observation and pattern recognition. In the Andes Mountains of South America, the Inca civilization developed its own astronomical traditions, though our knowledge of them is more limited because the Inca did not have a writing system in the conventional sense. Much of what we know about Inca astronomy comes from Spanish colonial accounts and from archaeological evidence, including the alignment of Inca buildings and the layout of their capital city, Cusco. The Inca divided the sky into regions and recognized both bright constellations formed by connecting stars, similar to Western constellations, and dark constellations formed by the dark dust clouds visible in the Milky Way. These dark constellations represented animals important to Andean culture, including a llama, a fox, a partridge, and a snake. The recognition of dark constellations as meaningful sky patterns was unique to Andean astronomy and reflected the visibility of the Milky Way in the dark skies of the high Andes. The Inca used astronomical observations for agricultural timing, particularly the heliacal rising of the Pleiades star cluster. The appearance of the Pleiades at dawn in June coincided with the beginning of the agricultural year in the Andes, marking the time to begin planting. The brightness and clarity of the Pleiades when they first became visible was also used to predict rainfall and crop success for the coming year, showing how astronomical observation connected with practical concerns. Inca architecture incorporated astronomical alignments. The Coricancha, the main temple in Cusco, had windows and sightlines aligned with the June solstice sunrise and other astronomical events. The city of Cusco itself was laid out according to astronomical and cosmological principles, with roads radiating from the Coricancha temple like rays from the sun. The Inca considered themselves children of the sun, and solar observations held special religious significance. The Inca used a system of sightlines called seeks that radiated from the Coricancha temple, connecting sacred sites called huacas. Some of these seekways were aligned with astronomical directions, including the rising and setting points of the sun at the solstices and equinoxes. This system integrated astronomy, geography, and religion into a comprehensive understanding of the relationship between the earthly and celestial realms. Earlier Andean civilizations also showed astronomical knowledge and interests. The Nazca culture, which flourished from approximately 100 before the Common Era to 800 in the Common Era, created enormous geoglyphs, lines and figures drawn on the desert surface that are best viewed from the air. Some researchers have suggested astronomical alignments for certain Nazca lines, though this interpretation remains controversial. The lines may have served multiple purposes, including astronomical, ceremonial, and processional functions. In what is now the southwestern United States, ancestral Pueblo peoples created astronomical markers and observatories. At Chaco Canyon in New Mexico, buildings show alignments with solar events. A famous site called the Sun Dagger uses 3 rock slabs to create changing patterns of light and shadow that mark the solstices and equinoxes on a spiral petroglyph. This device demonstrates sophisticated understanding of the sun's annual motion and the ability to mark it precisely. Chapter 8: Islamic Astronomy, Preserving and Extending Ancient Knowledge. Following the classical period, the center of astronomical research shifted to the Islamic world. From the 8th through the 15th centuries, Islamic astronomers preserved ancient Greek and Indian astronomical texts, made important observations, and developed new mathematical techniques and instruments. This period, often called the Islamic Golden Age, was crucial for the transmission of ancient astronomical knowledge to later European astronomers. The translation movement began in earnest during the Abbasid Caliphate, particularly under Caliph al-Ma'mun in the early 9th century. Greek astronomical texts, including Ptolemy's Almagest, were translated into Arabic, along with Indian astronomical works like the Surya Siddhanta. These translations preserve knowledge that might otherwise have been lost and made it accessible to Arabic-speaking scholars across a vast geographic area stretching from Spain to Central Asia. Islamic astronomers did not merely preserve ancient texts, but actively critiqued and attempted to improve them. They recognized problems in Ptolemaic astronomy, particularly the equant, which seemed to violate the principle of uniform circular motion. Islamic astronomers sought to create alternative models that would maintain the predictive accuracy of Ptolemaic astronomy while using only truly uniform circular motions, though they never fully succeeded in this goal within the geocentric framework. Al-Khwarizmi, who lived during the early 9th century, was one of the first major Islamic astronomers. His astronomical tables, the Zaij al-Sindhind, were based on Indian sources but adapted for Islamic use, including the conversion of dates to the Islamic calendar. Al-Khwarizmi's name gives us the word algorithm, and his work on algebra provided mathematical tools that would be essential for astronomical calculations. Al-Battani, who lived from approximately 858 to 929, made important astronomical observations and calculations. He determined the length of the solar year as 365 days, 5 hours, 46 minutes, and 24 seconds, very close to the modern value. He also improved Ptolemy's measurements of the inclination of the ecliptic and the precession of the equinoxes. His astronomical tables were influential in both the Islamic world and later in Europe, where they were translated into Latin. Ibn Yunus, who worked in Cairo around the year 1000, compiled extensive astronomical tables called the Hakimi Zij. These tables contained parameters for calculating planetary positions and included observations of eclipses and planetary conjunctions. Ibn Yunus's work showed the high level of observational accuracy achieved by Islamic astronomers and their systematic approach to compiling and organizing astronomical data. Al-Biruni, who lived from 973 to after 1050, was a polymath whose interests included astronomy, mathematics, geography, and history. He wrote extensively on astronomy and created his own astronomical tables. Al-Biruni was familiar with both Ptolemaic Greek astronomy and Indian astronomical traditions, and he attempted to synthesize and compare different astronomical systems. His discussion of the possibility of the Earth's rotation shows the intellectual openness of Islamic astronomical thought. The construction of large observatories was a notable feature of Islamic astronomy. These observatories, equipped with large instruments for measuring celestial positions, allowed for observations of unprecedented precision. The observatory built by Al-Mamun in Baghdad in the early 9th century was the first of these major facilities. It established a model for later Islamic observatories that combined observation, calculation, and library resources. The most famous Islamic observatory was built by Ulugh Beg in Samarkand in the early 15th century. This observatory featured a massive mural sextant, a quarter-circle instrument built into the ground with a radius of approximately 130 feet. This large size allowed for extremely precise measurements of stellar and planetary positions. Ulugh Beg's star catalogue, based on observations made at this observatory, contained positions for 1,018 stars, measured with greater accuracy than any previous catalogue. Islamic astronomers developed and refined astronomical instruments. The astrolabe, known in antiquity, was perfected by Islamic instrument makers into a sophisticated device for solving astronomical and timekeeping problems. The astrolabe could determine the time from the position of the sun or stars, find the direction to Mecca for prayer, and solve various other astronomical calculations. Beautifully crafted astrolabes became prized possessions of scholars and wealthy patrons. The quadrant, another Islamic astronomical instrument, was used to measure the altitude of celestial bodies above the horizon. Large mural quadrants, permanently mounted on walls, allowed for precise measurements. Islamic astronomers also developed the torquetum, a complex instrument for converting between different astronomical coordinate systems, showing their sophisticated understanding of spherical geometry and coordinate transformations. Islamic astronomy served important practical functions within Islamic society. Determining the times for the 5 daily prayers required knowledge of the sun's position, which varied throughout the year. Finding the direction to Mecca from locations across the Islamic world required geographic and astronomical knowledge. Creating an accurate calendar, particularly for determining the dates of Ramadan and other religious observances, required precise understanding of lunar phases and solar motion. The mathematical developments in Islamic civilization supported astronomical work. Arabic numerals, including the crucial concept of zero, made calculations much easier than with Roman numerals. Trigonometry, building on Indian and Greek foundations, was extensively developed by Islamic mathematicians. Algorithms for solving astronomical problems were refined and systematized. This mathematical infrastructure was essential for the computational astronomy practiced in the Islamic Golden Age. Islamic astronomers also made cosmological contributions. Al-Farabi, who lived in the 10th century, wrote about the structure of the cosmos and the nature of celestial bodies. Ibn al-Haytham, known in the West as Al-Hazan, who lived around 965 to 1040, critiqued Ptolemaic astronomy and proposed alternatives, though he too struggled with the equant problem. His work on optics also had implications for understanding how we see celestial bodies and how atmospheric refraction affects observations. The Maraga school, based in an observatory built in Maraga, Persia, in the 13th century, developed sophisticated astronomical models. Nasir al-Din al-Tusi and his colleagues created the Tusi couple, a mathematical device using two circular motions to produce linear motion. This and similar techniques allowed them to construct planetary models without the equant while maintaining predictive accuracy. These models would later influence European astronomers, possibly including Copernicus. Ibn al-Shatir, who worked in Damascus in the 14th century, created planetary models that were mathematically equivalent to later Copernican models in their geometric structure, though they maintained a geocentric framework. The similarity between Ibn al-Shatir's models and Copernicus's has led historians to investigate possible transmission of Islamic astronomical ideas to Renaissance Europe, though the exact channels of transmission remain unclear. The decline of Islamic astronomy began in the 15th and 16th centuries as political instability affected major centers of learning. However, by this time, Islamic astronomical knowledge had already begun to reach Europe through translations, particularly in Spain, where Islamic and Christian cultures interacted. The translation of Islamic astronomical texts into Latin in the 12th and 13th centuries was crucial for the development of European astronomy in the Renaissance. Chapter 9: Common Themes and Methods in Ancient Astronomy. Despite developing in isolation from one another, ancient astronomical traditions showed remarkable similarities in their approaches and concerns, reflecting universal human responses to the celestial realm. The most fundamental commonality was careful observation. Regardless of their theoretical frameworks or cultural contexts, ancient astronomers were, above all, patient observers. They watched the skies night after night, year after year, generation after generation, slowly accumulating knowledge about celestial patterns and regularities. This observational foundation was essential for developing calendars, predicting astronomical events, and creating cosmological models. Record keeping was another universal practice. Whether on clay tablets in Mesopotamia, on papyrus in Egypt, on paper in China, or in stone inscriptions in the Americas, ancient astronomers documented their observations and calculations. These records allowed knowledge to accumulate across generations and enabled astronomers to discover long-term patterns that would not be apparent within a single human lifetime, such as the precession of the equinoxes or the Saros eclipse cycle. Mathematical analysis of astronomical data was crucial across cultures. Ancient astronomers recognized numerical patterns in celestial motions and used mathematics to describe and predict these patterns. From Babylonian arithmetical sequences to Greek geometric models to Indian trigonometric calculations, mathematics provided a language for expressing astronomical knowledge and making predictions. The development of mathematics and astronomy were closely intertwined throughout the ancient world. Calendrical functions drove much ancient astronomy. Agricultural societies needed to know when to plant and harvest crops. Religious ceremonies needed to be performed at appropriate times. Administrative functions required consistent timekeeping. These practical needs motivated careful observation of the sun, moon, and stars, leading to the development of increasingly sophisticated calendar systems that balance the incommensurate cycles of the day, lunar month, and solar year. The interpretation of celestial events as omens or divine messages was nearly universal in ancient astronomy. From Mesopotamian astrology to Chinese celestial divination to Maya calendar divination, astronomical knowledge was used to interpret the will of the gods or the patterns of cosmic order as they applied to human affairs. While this astrological dimension of ancient astronomy differs from modern scientific astronomy, it provided cultural motivation and institutional support for sustained astronomical observation and analysis. Architectural alignments with astronomical events appear across ancient cultures. Temples, tombs, and other significant structures were often oriented towards celestial directions or aligned with solar or stellar events. These alignments served multiple functions. They connected earthly structures with cosmic order, they marked important times of year, and they demonstrated the rulers' or priesthoods' mastery of astronomical knowledge. From Egyptian pyramids to Maya temples to Stonehenge, architecture and astronomy were intimately connected. The development of astronomical instruments represents another common theme. Ancient astronomers created tools to improve the precision of their observations and to perform astronomical calculations. Gnomons, water clocks, armillary spheres, astrolabes, and other instruments appeared across different cultures, sometimes independently invented and sometimes transmitted through cultural contact. These instruments embodied astronomical knowledge and extended human observational capabilities. Cosmological speculation about the nature and structure of the universe was universal. Ancient astronomers asked fundamental questions. What is the Earth's shape? How far away are celestial bodies? What causes celestial motions? Different cultures proposed different answers, from the cosmic egg of Chinese Huntian theory to the nested spheres of Greek cosmology to the layered heavens of Indian cosmology. These cosmological models attempted to make sense of the observable heavens within broader philosophical and religious frameworks. The concept of cycles and periodicity was central to ancient astronomical thinking. Ancient astronomers recognized that celestial phenomena repeat in predictable patterns. The daily rotation of the stars, the monthly phases of the moon, the annual motion of the sun through the zodiac, the longer cycles of planetary motions and eclipses. Identifying and measuring these cycles was a major achievement of ancient astronomy and enabled the prediction of future celestial events. Cultural exchange and transmission of astronomical knowledge occurred throughout the ancient world. Though the extent and routes of transmission varied, Babylonian astronomy influenced Greek astronomy. Indian astronomy spread to Southeast Asia and influenced Islamic astronomy. Islamic astronomy transmitted ancient knowledge to medieval Europe. Chinese astronomy had some exchange with Indian astronomy. These interactions enriched astronomical traditions and allowed useful techniques and observations to spread across cultures. The social position of astronomers varied across cultures, but generally involved close association with political or religious power. court astronomers in Mesopotamia and China, temple priests in Egypt, philosopher-scientists in Greece, and priest astronomers in the Americas all held positions of authority and prestige. Astronomical knowledge was often esoteric, restricted to specialized practitioners who had undergone long training. This elite knowledge conferred social status and political influence. Ancient astronomy shows the development of specialized technical vocabulary and notation systems. Astronomical concepts required precise terminology, and different cultures developed their own technical language for describing celestial phenomena, coordinate systems, and mathematical techniques. This specialized language allowed for precise communication among astronomers and for the preservation and transmission of technical knowledge through texts and teaching. The limitations of naked eye observation imposed constraints on ancient astronomy that would not be overcome until the telescope was invented in the early 17th century. Ancient astronomers could not see the moons of Jupiter, the rings of Saturn, or the countless faint stars invisible to the unaided eye. They could not perceive the phases of Venus that would provide strong evidence for the Copernican heliocentric model. These observational limitations meant that ancient astronomers worked with incomplete information, yet they achieved remarkable results within these constraints. Error and approximation were inherent in ancient astronomy. Measurements had limited precision. Mathematical models were approximations of reality, and theoretical frameworks were based on incomplete understanding. Yet, ancient astronomers recognized and attempted to minimize error, refining their observations, improving their instruments, and developing more sophisticated mathematical techniques. The progressive improvement of astronomical knowledge over centuries shows the self-correcting nature of astronomical research, even in the ancient world. Chapter 10: Stonehenge and Prehistoric European Astronomy. While we cannot read the thoughts of the people who built these monuments, the alignments encoded in stone structures provide evidence of careful astronomical observation and suggest that such knowledge was important enough to warrant massive communal effort. Stonehenge, located on the Salisbury Plain in southern England, is perhaps the most famous prehistoric monument in the world. The site was constructed in several phases over approximately 1500 years, from around 3000 before the Common Era to 1500 before the Common Era. The monument we see today represents the culmination of this long building process, and it incorporates astronomical alignments that suggest its builders had sophisticated understanding of solar and lunar cycles. The most famous alignment at Stonehenge is with the summer solstice sunrise. On the longest day of the year, the sun rises above the heel stone, a large sarsen stone standing outside the main monument when viewed from the center of the stone circle. This alignment is so precise that it cannot be coincidental and must have been intentionally incorporated into Stonehenge's design. The winter solstice sunset is also marked, aligned in the opposite direction along the same axis. The avenue, a processional way leading to Stonehenge, is aligned with the solstice axis, suggesting that ceremonies involving processions along this path may have been timed to coincide with the solstices. The importance of the solstices in the monument's design tells us that the builders were concerned with marking the extremes of the sun's annual motion and perhaps with celebrating these turning points in the solar year. Some researchers have proposed that Stonehenge also incorporates alignments related to the moon's cycles. The moon's motion is more complex than the sun's, with the positions of moonrise and moonset varying not just over the course of a month, but over a cycle of approximately 18.5 years. The extremes of this cycle, called the major and minor lunar standstills, may be marked by certain alignments at Stonehenge, though this interpretation remains more controversial than the solar alignments. The effort required to construct Stonehenge was immense. The sarsen stones, the large stones forming the outer circle and the trilithons, weigh up to 25 tons each and were transported from quarries about 20 miles away. The bluestones, though smaller, were transported from the Preseli Hills in Wales, a distance of about 140 miles. The astronomical significance of the monument must have been profound to justify such extraordinary effort. Other megalithic monuments in Britain and Ireland show astronomical alignments. Newgrange, a passage tomb in Ireland built around 3200 before the Common Era, is aligned so that the winter solstice sunrise illuminates the inner chamber through a roof box above the entrance. For a few minutes each year, light penetrates deep into the tomb, illuminating the chamber in a spectacular display that connects death and burial with the rebirth of the sun after the darkest time of year. The Ring of Brodgar in Orkney, Scotland, is a large stone circle that may have incorporated multiple astronomical alignments, including markers for both solar and lunar events. The standing stones of Callanish on the Isle of Lewis form a cross shape with a central circle, and various alignments with solar and lunar events have been proposed. These monuments suggest that astronomical observation was important across Neolithic Britain. The Nebra sky disk, discovered in Germany and dating to around 1600 before the Common Era, provides direct evidence of Bronze Age European astronomical knowledge. This bronze disk is decorated with gold symbols representing the sun or full moon, a crescent moon, and stars including a cluster, interpreted as the Pleiades. The disk may have been used to harmonize solar and lunar calendars, with the angle between the crescent moon and the Pleiades indicating when to add an intercalary month. The astronomical knowledge evidenced by these monuments existed without written records, preserved instead through oral tradition and encoded in enduring stone structures. The precision of the alignments shows that astronomical observations were made carefully and consistently over long periods. The incorporation of these alignments into monuments that required massive communal effort demonstrates that astronomical knowledge had significant cultural and religious importance. The purposes of these astronomical alignments likely included multiple functions. Marking the seasons would have had practical agricultural applications, helping communities know when to plant and harvest. Religious and ceremonial functions seem evident from the monumentality of the structures and from their association with burials. The alignments may also have served to demonstrate and reinforce the authority of those who possessed astronomical knowledge and could predict celestial events. We should be cautious about attributing too much astronomical sophistication to megalithic monument builders based solely on alignments, as the interpretation of such alignments can be subjective and selective. However, the most clear and precise alignments, particularly the solstice alignments at Stonehenge and Newgrange, strongly suggest intentional incorporation of astronomical knowledge into monument design. The astronomical alignments in megalithic monuments raise questions about how this knowledge was acquired and transmitted. Without writing, astronomical knowledge would have been passed down through oral teaching and through observation at the monuments themselves. Certain individuals or groups within the society must have been responsible for maintaining this knowledge and for determining when important celestial events would occur. Chapter 11. North American Indigenous Astronomy. The indigenous peoples of North America, though diverse in their cultures and environments, shared interests in observing and interpreting celestial phenomena. From the Arctic to the southwest, from the Great Plains to the eastern woodlands, Native American peoples watched the skies and incorporated astronomical knowledge into their cultural practices, though most of this knowledge was transmitted orally rather than through written records. The ancestral Puebloans of the American Southwest created various astronomical markers. At Chaco Canyon in New Mexico, several buildings show alignments with solar events. Casa Rinconada, a great kiva dating to around 1100 in the Common Era, has windows that may have been aligned with the summer solstice sunrise. The architectural sophistication of Chaco Canyon suggests a society with advanced understanding of engineering, agriculture, and timekeeping. The Sundagger site at Fajada Butte in Chaco Canyon provides a particularly striking example of astronomical marking. 3 stone slabs lean against a cliff face, and petroglyphs are carved on the cliff behind them. At the summer solstice, a dagger of light passes through the center of a spiral petroglyph. At the winter solstice, 2 daggers of light bracket the same spiral. At the equinoxes, a smaller dagger of light passes through a smaller spiral. This device marks all 4 major solar events of the year with precision. The creation of the sun dagger required careful observation of the sun's motion over at least 1 full year, and probably multiple years to ensure the alignment was correct. The choice to mark these alignments with petroglyphs in a location requiring effort to reach suggests that these solar events held religious or ceremonial significance, not merely practical importance for calendar keeping. The Bighorn Medicine Wheel in Wyoming is another site showing possible astronomical alignments. This wheel consists of a central cairn with 28 spokes radiating outward to a circular rim, with additional cairns around the rim. Some researchers have proposed that the wheel's alignments mark the summer solstice sunrise and sunset, as well as the rising points of certain bright stars. The 28 spokes may represent the days of the lunar month, showing integration of lunar and solar observations. Plains peoples like the Lakota, Pawnee, and Blackfeet had rich traditions of celestial observation and interpretation. The Pawnee, in particular, are noted for their sophisticated star knowledge, with celestial bodies playing important roles in their religious ceremonies and mythology. Villages were sometimes laid out according to celestial patterns, and the timing of ceremonies was coordinated with the appearance of certain stars and constellations. The Pawnee recognized numerous individual stars and star groups, giving them names and associating them with various spirits and powers. The morning star and evening star, both the planet Venus, held particular importance in Pawnee religion. The Pleiades star cluster was observed and played a role in timing certain ceremonies. The Pawnees' familiarity with the night sky was sophisticated and detailed, reflecting generations of careful observation. In the Pacific Northwest, indigenous peoples like the Haida, Tlingit, and Salish had astronomical knowledge reflected in their oral traditions and ceremonial practices. The timing of ceremonies was sometimes coordinated with celestial events. Oral traditions included stories about the sun, moon, and stars, encoding astronomical knowledge in narrative form. The importance of salmon runs in Pacific Northwest cultures meant that seasonal timing was crucial, and celestial observations helped mark the changing seasons. The Chumash people of Southern California had astronomical knowledge reflected in their rock art and oral traditions. Some rock art sites may show astronomical symbols or alignments. The Chumash were accomplished seafaring people, and their navigation of the California coast and trips to the Channel Islands required knowledge of stellar navigation. The timing of solstices and the appearance of certain stars helped mark the Chumash calendar. Arctic peoples like the Inuit and Yupik lived at high latitudes where the sun's behavior differs dramatically from lower latitudes. The long summer days when the sun barely sets and the long winter nights when it barely rises created a different relationship with solar cycles. The Arctic winter night sky, with aurora borealis dancing overhead and the stars visible for extended periods, provided excellent opportunities for astronomical observation. Inuit knowledge of stars and constellations was extensive. Individual stars, star clusters, and constellations were named and used for navigation and timekeeping. The appearance and position of certain stars indicated the seasons and the appropriate times for various subsistence activities. The North Star, which remained nearly fixed in position while other stars rotated around it, was particularly important for navigation. The Iroquois peoples of the eastern woodlands had celestial traditions including the Pleiades, which they called the Seven Sisters or the Seven Dancers. The appearance of the Pleiades at certain times of year marked seasonal changes. The Iroquois observed solar and lunar eclipses, and these events often featured in oral traditions and were interpreted as significant supernatural occurrences. Many Native American cultures had creation stories involving celestial bodies, or explaining how certain stars and constellations came to be in the sky. These stories served multiple functions. They encoded astronomical knowledge in memorable narrative form. They connected celestial patterns with cultural values and beliefs, and they provided explanations for why the sky appears as it does. The stories were transmitted orally from generation to generation, preserving astronomical knowledge without written records. The timing of ceremonies and festivals in many Native American cultures was coordinated with celestial events. The Sundance of Plains peoples was timed to the summer solstice. Various harvest ceremonies coincided with the autumnal equinox or with the appearance of certain stars. Winter solstice ceremonies marked the return of the sun and the promise of spring. These ceremonial cycles connected human activities with cosmic cycles. Seasonal round activities in hunter-gatherer and agricultural societies required knowledge of the changing seasons. The first appearance of certain stars at dawn or dusk, the changing position of the setting sun along the horizon, the phases of the moon, these celestial markers, helped indigenous peoples know when to plant and harvest crops, when to hunt certain animals, when to gather particular plant foods, and when to move to different seasonal camps. The survival of indigenous astronomical knowledge to the present day has been impacted by colonization, forced cultural assimilation, and the disruption of traditional lifestyles. Much astronomical knowledge was lost as elders died without passing on their knowledge, and as younger generations were prevented from learning traditional practices. However, there is growing interest in preserving and revitalizing indigenous astronomical knowledge as part of broader efforts to maintain indigenous cultures and languages. Contemporary researchers working with indigenous communities have documented surviving astronomical knowledge, recording star names, constellation patterns, and the uses of astronomical observations in traditional practices. This collaborative work shows both the sophistication of indigenous astronomical knowledge and the importance of oral tradition in preserving and transmitting such knowledge across generations. Chapter 12. The Synthesis of Astronomical Traditions. The history of astronomy is not a series of isolated developments, but a complex web of cultural exchanges, transmissions, and syntheses that created increasingly sophisticated understanding of the heavens. The ancient Near East saw extensive interaction between different astronomical traditions. Babylonian astronomical texts influenced Assyrian, Persian, and eventually Greek astronomy. The conquest of Babylon by various empires facilitated the spread of Babylonian astronomical knowledge. When Alexander the Great conquered the Persian Empire in the 4th century before the Common Era, he brought Greek and Near Eastern cultures into direct contact, setting the stage for the Hellenistic synthesis of astronomical knowledge. Alexandria in Egypt became a major center where Greek, Egyptian, and Babylonian astronomy intersected. The Library of Alexandria collected astronomical texts from across the known world. Greek astronomers in Alexandria had access to Babylonian observational records spanning centuries, allowing them to discover long-term cycles like the precession of the equinoxes. They also encountered Egyptian calendar systems and timekeeping methods, incorporating useful elements into their own astronomical practice. The Ptolemaic astronomical system synthesized Greek geometric models with Babylonian numerical parameters. Ptolemy had access to Babylonian observational records and used them to derive parameters for his planetary models. The Almagest contains Babylonian observations alongside Greek and more recent Alexandrian observations, showing how astronomical knowledge accumulated across cultures and centuries. This synthesis created a comprehensive system more powerful than either the Greek or Babylonian tradition alone. In India, there was interaction between indigenous astronomical traditions and incoming Greek astronomy following Alexander's campaigns that reached the borders of India. Greek astronomical texts were translated into Sanskrit, and Indian astronomers engaged with Greek ideas while maintaining their own distinct methods and cosmological frameworks. The result was a uniquely Indian astronomical tradition that drew on multiple sources while remaining rooted in Indian mathematical and philosophical approaches. Buddhist monks traveling along the Silk Road carried astronomical knowledge between India and China. Chinese astronomers became aware of some Indian astronomical methods and concepts, though Chinese astronomy remained largely distinct from Indian astronomy. The transmission was limited and selective, with Chinese astronomers adopting specific techniques while maintaining their overall approach to celestial observation and interpretation. The Islamic Golden Age represented the most extensive synthesis of astronomical traditions in the ancient and medieval world. Islamic astronomers had access to Greek texts through translations from Greek and Syriac into Arabic. They also encountered Indian astronomical works through translations from Sanskrit. Persian astronomical traditions contributed to the mix. Islamic astronomers synthesized these diverse sources while conducting their own observations and developing new mathematical techniques. The result of this Islamic synthesis was an astronomical tradition that incorporated the best elements from Greek, Indian, and Persian sources, while surpassing all of them in observational precision, mathematical sophistication, and comprehensiveness. Islamic observatories used large instruments to make precise measurements. Islamic mathematicians developed spherical trigonometry to a high level. Islamic astronomical tables incorporated vast amounts of observational data and computational work. The transmission of Islamic astronomy to medieval Europe beginning in the 12th century brought this synthesized knowledge to Christian scholars. Latin translations of Arabic astronomical texts, often themselves translations from Greek or Sanskrit, made the accumulated astronomical knowledge of multiple civilizations available to European scholars. This transmission was crucial for the later development of Renaissance astronomy and the scientific revolution. Some astronomical traditions developed in relative isolation and show limited influence from other traditions. Maya astronomy in the Americas developed independently of Old World astronomy, creating unique approaches to calendars and astronomical observation. The Maya independently discovered the same celestial cycles that Babylonian astronomers had found, showing that careful observation leads to similar discoveries regardless of cultural context. Yet even in the Americas, there was some transmission of astronomical knowledge between different cultures. The calendar systems of the Maya, Aztec, and other Mesoamerican peoples shared common elements, suggesting either a common origin or cultural exchange. The Inca in South America had different astronomical traditions from Mesoamerican peoples, reflecting their isolation from Mesoamerican cultures, yet some broad similarities in approach suggest universal aspects of how human societies engage with the night sky. The preservation of ancient astronomical knowledge depended on several factors. Texts needed to be copied and recopied as fragile materials decayed. Libraries and schools needed to maintain collections and continue teaching. Astronomical instruments and observational techniques needed to be passed down through training. When these transmission mechanisms failed, knowledge could be lost, sometimes irretrievably. The burning of the Library of Alexandria, occurring in multiple incidents over several centuries, destroyed many unique texts. The destruction of Maya codices by Spanish conquistadors and missionaries eliminated most written records of Maya astronomy, with only 4 codices surviving to the present. Political upheavals, invasions, and cultural disruptions throughout history have caused the loss of astronomical texts and knowledge. What survives represents only a fraction of ancient astronomical work. The recovery of lost astronomical knowledge sometimes occurred through archaeological discoveries. Clay tablets with cuneiform astronomical texts buried for millennia have been excavated in Mesopotamia. Astronomical instruments found in ancient shipwrecks, like the Antikythera mechanism, reveal technological sophistication that was unknown from textual sources alone. Archaeological astronomy, the study of astronomical alignments in ancient structures, reveals knowledge that was encoded in architecture rather than texts. The reinterpretation of surviving texts as scholarly methods and knowledge have advanced also contributes to recovering ancient astronomical knowledge. Texts that were previously misunderstood or only partially comprehended become clearer as researchers develop better understanding of ancient languages, mathematical notations, and observational methods. This ongoing work of interpretation means that our understanding of ancient astronomy continues to evolve. Modern astronomy has benefited from ancient astronomical records in unexpected ways. Chinese records of supernovae and comets provide data about celestial events that occurred centuries ago, allowing modern astronomers to study the long-term behavior of these objects. Babylonian eclipse records help refine our understanding of the Earth's rotation, which has been gradually slowing over time. Ancient observations contribute to contemporary astronomical research, giving ancient data continuing scientific value beyond historical interest. As we conclude our journey through the astronomical traditions of ancient civilizations, we can appreciate the remarkable achievements of our ancestors as they sought to understand the heavens above them, from the plains of Mesopotamia to the Nile Valley, from the mountains of Greece to the jungles of Central America, from the Indian subcontinent to the observatories of the Islamic world. Human beings looked up at the night sky and tried to make sense of what they saw. Ancient astronomers gave us the calendar systems we still use, divided into years, months, and days. They identified the constellations that still guide our navigation of the night sky. They developed mathematical techniques that remain fundamental to astronomy and mathematics. They created instruments and observational methods that would be refined but not fundamentally replaced until the modern era. They asked questions about the nature and structure of the universe that we continue to investigate with more powerful tools. The knowledge accumulated by ancient astronomers was not merely academic. It served practical functions in agriculture, timekeeping, and navigation. It supported religious and political institutions. It satisfied human curiosity about the cosmos and our place within it. Ancient astronomy was integrated into the fabric of ancient societies in ways that modern specialized science is not, touching nearly every aspect of life, from planting crops to planning religious festivals to legitimizing political authority. We should also recognize what ancient astronomy was not. It was not modern science with its emphasis on testable hypotheses, experimental verification, and mechanistic explanation. Ancient astronomy combined careful observation and mathematical analysis with religious interpretation and philosophical speculation in ways that would be considered methodologically problematic in modern science. Yet this integration reflects the holistic worldviews of ancient cultures, in which knowledge was not divided into separate disciplinary silos. The transmission of astronomical knowledge across cultures and across time shows both continuity and transformation. Each culture that received astronomical knowledge from another adapted it to local needs and frameworks, neither simply accepting it unchanged nor rejecting it entirely. This process of cultural transmission and adaptation enriched astronomical knowledge and allowed useful techniques and observations to spread widely, while also producing diverse astronomical traditions reflecting different cultural values and priorities. The astronomical achievements of ancient civilizations remind us that scientific and mathematical sophistication is not unique to modern Western civilization. The Babylonians, Chinese, Indians, Maya, and others developed complex mathematical astronomy without benefit of modern tools or scientific methods. They achieved results that command respect even from our modern vantage point. Their work shows that intellectual achievement flourishes in many cultural contexts, and that the desire to understand the cosmos is deeply human. Many specific achievements of ancient astronomy were lost and had to be rediscovered. The heliocentric model proposed by Aristarchus, the accurate Earth measurements of Eratosthenes, the sophisticated mathematical models of Islamic astronomers, these and other achievements were forgotten or ignored for centuries before being revived or reinvented. The history of astronomy is not a simple story of linear progress, but includes dead ends, lost knowledge, and rediscoveries, reminding us that scientific knowledge is fragile and depends on continued transmission and cultivation. The aesthetic dimension of ancient astronomy should not be overlooked. The constellations with their mythological associations, the architecture aligned with celestial events, the beautiful instruments crafted by skilled artisans, these show that ancient astronomy engaged human creativity and artistic sensibility alongside mathematical and observational skills. The night sky was not just an object of scientific study, but a source of wonder, beauty, and meaning. As we think about ancient astronomers looking up at the same stars we see today, we can feel a connection across the millennia. The Big Dipper looked the same to Babylonian astronomers as it does to us, though they called it by different names and wove different stories around it. The moon went through the same phases for Egyptian priests as it does for us. This continuity of celestial phenomena across human history provides a shared reference point connecting ancient and modern sky watchers. Yet we should also recognize how much our understanding has changed. Ancient astronomers believed the Earth was the center of the cosmos, that celestial bodies were fundamentally different from earthly matter, that the stars were attached to a sphere surrounding the Earth. Modern astronomy has revealed a universe vastly larger and older than ancient astronomers imagined, with the Earth as a small planet orbiting an ordinary star in one galaxy among billions. This transformation in understanding represents one of the great intellectual achievements of human civilization. The methods of ancient astronomy, careful observation, mathematical analysis, instrument development, theoretical modeling remain central to modern astronomy, even as the specific theories and technologies have advanced tremendously. In this sense, ancient astronomers were not doing something fundamentally different from modern astronomers. They were engaged in the same enterprise of trying to understand the cosmos through systematic observation and rational analysis, working with the tools and knowledge available to them. The integration of astronomy with timekeeping, agriculture, religion, and governance in ancient civilizations shows how knowledge can serve multiple functions simultaneously. Astronomical observations served practical needs like planting crops at the right time, while also addressing spiritual needs for understanding humanity's place in the cosmos and political needs for legitimizing authority through mastery of esoteric knowledge. This multifunctionality made astronomy central to ancient civilizations in ways that are sometimes hard to appreciate in our modern context of specialized knowledge. The diversity of ancient astronomical traditions, from Babylonian mathematical astronomy to Chinese bureaucratic astronomy, to Maya calendrical astronomy to Greek geometric astronomy, shows that there are multiple approaches to understanding the heavens. No single tradition possessed a monopoly on astronomical truth. Each contributed unique insights and methods. The eventual synthesis of different traditions, as occurred in Islamic astronomy, which drew on Greek, Indian, and Babylonian sources, produced richer understanding than any single tradition could have achieved in isolation. And so, our journey through ancient astronomy comes to a close. We have travelled across continents and millennia, exploring how different civilizations observed the heavens and created systems of astronomical knowledge. We have seen careful observation, mathematical brilliance, theoretical innovation, and cultural diversity in the human quest to understand the cosmos. As you drift off to sleep, let these ancient sky watchers accompany you into dreams, their patient observations and profound questions echoing through the ages. Thank you for joining us on Sleepless History. May your dreams be filled with stars and the ancient astronomers who watched them. Good night.